NMR. I can't think of three things for the bit. So how does it work? Let's find out. All subatomic particles spin, and you can think of them as a spinning sphere, because that's the easiest way to do it. And because they spin, they have an angular acceleration and an angular momentum, and these values can be used to find the spin of the particle. So for an electron, magnitude of spin is equal to the Planck's constant times, this is something called the quantum momentum number, which we're working out here, times the quantum momentum number plus 1. And if you do a really long derivation, you get root 3 over 2 Planck's constant. And so you can obviously solve this for this. So you get S equals half, and you can sub that back into there, and you get the spin of the electron. So the total spin of the nucleus depends on the spin of any nucleons, and all the nucleons will have the same spin value as an electron, which is a half. But where it gets difficult is when they start to pair, the S values begin to cancel out. So your I value can either be a half or it can be an integer. So if the number of protons and the number of neutrons are both even, your value becomes 0, and that means the nucleus has no spin. But if they're unpaired, it gives the particle a spin. They can have high energy spins or they can have low energy spins. The energy value all depends on the makeup of the protons, so the quarks and things, and I'm definitely going to make a video on that in the future because that was very complicated to read and research on. But obviously, a non-zero spin value means a non-zero magnetic dipole. And then when you have a non-zero spin, you times it by the gyromagnetic ratio, which is so fun to say, and it's equal to the magnetic field. So these two are directly proportional to each other. So obviously, when you're doing NMR, you want things with an odd number of nucleons. So things like carbon-13 or hydrogen are really useful. So you take your sample and you bung it in a strong permanent magnetic field. And when I say strong, we're talking 20 Teslas. When I went to Queen Mary's University, they had one of these, and they had a massive line all the way around the building where you could not step in because it would literally just pull you in or interfere with your phone. And the samples need to be kept in extreme conditions. We're talking 3 Kelvin. And they use liquid hydrogen, but because it's so expensive, they tend to top up liquid hydrogen less often and cool it using liquid nitrogen, which is cheaper. Now, magnetic fields can be parallel, so they're low energy, or they can be anti-parallel, meaning they have high energy. And what that means is there has to be a gap in the middle where it's kind of not anything. So they send a bunch of radio waves into the machine. From there, you get the change in energy is equal to Planck's constant times the frequency of the radio waves, which is equal to the gyromagnetic ratio times the magnetic flux density. And in this magnetic field, particles precess, that is, orbit around the magnetic field. The absorbed energy causes particles to shift levels, and then after that, they undergo relaxation, that is, return to their original position. And this can occur one of two ways, either T1 or T2. T1, like I said, they just return to their original orbit, whereas in T2, they begin to fall out of sync with all their other particles, which minimizes the overall spin. Now, it's not unreasonable to think that all atoms would have the same energy value, but this isn't true because of shielding and electron shells. Now, the energy given, rather than in joules, is measured in parts per million, because the value is so low, and that's what appears on your NMR spectroscope. NMR can be used to find the formula, structure, or the purity of a sample. So there you go, I hope you enjoyed. Please feel free to like and subscribe, and join me next week where we'll be talking about plastics. Thanks, bye.